Hi everyone, it's Dr. Marks, and our topic for today is the t-distribution. Now, this is not going to be the most exciting of content for this class, but we have to understand the t-distribution because we are going to be using it for the rest of the semester. This won't be super long, so make sure you're clear on this idea, and we're going to be applying it for many lessons. All right. Quick overview. In the last lesson, if you recall, we explored the law of large numbers and we talked about the central limit theorem, right? Really powerful things in statistics. So we said as n increases, right, our number of observations increase, the distribution of our sample means converged to the normal distribution. All right, that's a lot of words. Let's make sure we remember what that means. So we have a population, right? And from that population, we're going to take samples. So we have a population. Let's take a bunch of samples. For each sample, let's calculate a mean. Now, with my collection of means, I'm going to form a distribution. And it turns out that that distribution converges to the normal distribution as I have more and more of these sample means, as my n increases. So why do we care about the normal distribution? We've also talked about this a little bit. Assuming that our data is normally distributed, well, that means we know the properties of the distribution, right? Think about that normal distribution that we looked at last lesson. In that last lesson, we looked at that bell-shaped curve and we said, okay, there's certain things we know about the normal distribution. Remember we said, okay, if we look at plus or minus 2 standard deviations from the mean, we're going to have 95% of the observations. We can be 95% certain that an observation would fall into that range. That's a property of our normal distribution. So we can use those properties in order to assess the likelihood of some outcome. So we're back to that thing we've talked about before, kind of this level of certainty. So how likely is something? How certain are we that something is true? And this gives us a way of determining if one hypothesis is more plausible than another hypothesis. And to do this, we can use a t-distribution. Now that t-distribution is going to be very helpful when our sample sizes are smaller. You're going to see that as our sample sizes grow, that t-distribution is going to start looking like the normal distribution. But smaller numbers of observations, we're going to see that they look different. So in this graph here, we see our standard normal distribution, and then we see the t-distribution, right? And they look a little different, right? That t-distribution is shorter, it's fatter, right? That standard normal is taller, a little more shapely. If we're talking about a normal distribution describes a full population, right? But we're not always dealing with populations. A t-distribution describes samples drawn from a full population. So these are not going to be exactly the same things, right? So we normally are going to be drawing samples from a population. We're normally not going to be working with the population itself. So that t-distribution is going to be very helpful for that reason. We see if we look at both of these distributions, which now are down there in that bottom right corner, they're both symmetric, right? We see that. And remember, symmetry means the left and the right look exactly the same. We could fold them in half and it would line up exactly. They both have a mean of 0. They both have that smooth shape, but there are some differences. The normal distribution assumes that the standard deviation or the variance, right, they're related, of the population is known. So a normal distribution assumes that we know the standard deviation or variance of the population. But the t-distribution doesn't. For the t-distribution, it's not known, which means it has to be estimated. So we have this difference. They look different, right? As I said, I'm going to show you in a minute that they might get closer together as we have more observations, but one assumes that we know the standard deviation of the population, but with the t-distribution, we need to estimate. So again, the t-distribution is used when the population variance or the standard deviation, remember they're related to each other, one is the square root of the other or the square depending on which direction you're going. The t-distribution is used when the population variance or standard deviation is unknown. So estimating the variance from the sample, right? Remember, we're trying to learn about the population from the sample leads to greater uncertainty. Well, that makes sense, right? Because we're just trying to estimate. We don't know with certainty an exactness of the population variance, right? And so with greater uncertainty, it gives us a more spread out distribution. So look at that for a second. Is that what we see? A more spread out distribution with the t-distribution reflecting this greater uncertainty? Sure, it is. So this can be seen by the t-distribution's heavier tails. We have more weight in the tails, and that weight comes from the middle, right? So it's shorter and kind of wider, right? So we see these tails right there. The t-distribution is based on what we call degrees of freedom. And you've seen the idea of degrees of freedom before in one of our earlier modules, but it is a confusing concept. So I'm going to define it, and then I'm going to try to illustrate it for you, but we will work with degrees of freedom for the rest of the semester. So degrees of freedom is the number of values that are free to vary. The number of values that are free to vary when the value of some statistic is known. The number of values that are free to vary when the value of some statistic is known. That's a hard definition to get your brain around, in my opinion. It's just a little abstract. The number of values that are free to vary when the value of some statistic is known. Another way of explaining it is, it's the number of values that need to be known in order to know all of the values. I think that's a little bit easier. The number of values that need to be known in order to know all of the values. Either way, I agree with you because you're probably like, what? This is a confusing topic. So let me simply use an example because I think I can make this clear if we have one. So let's go back to our die that we've been using all semester. It's probably getting worn out. I've tossed this die so many times, right? And I'm going to roll it 5 times. Now, let's say we know 4 of these rolls, the outcomes of 4 of these rolls, but we also know the mean. And I have that information. We know the first roll, I roll a 2, and the second roll a 4, and the third roll a 6, the fourth roll a 5, but I don't know the 5th roll. I do, however, know the mean equals 3.6. So if I take all 5 observations, one of which I don't know, and I average it, I get 3.6. Now, can I solve for x sub 5? Yeah, I can solve for the 5th roll. So I'm just going to throw in my numbers here, add them all together, plus x5, that's the thing I'd need to solve for, and divide it by 5 because I'm taking the average, and I know the average is equal to 3.6. So if I add up all the rolls and I divide it by 5, you know that gives me a mean, so I don't mean to insult your intelligence, and I'm setting that equal to the mean that I know, 3.6. So I get 17 plus x5, all divided by 5, is equal to 3.6. Well, if you do some simple math, you can figure out that x5 has to be 1. On my 5th roll, I rolled a 1. So the bottom line is, if I know 5 values, then I know the last value is x5. So that's the idea of thinking about degrees of freedom, and it's confusing. We're generally going to have an equation for calculating degrees of freedom. So with most of our applications, we're going to know how to calculate degrees of freedom. There's just a little simple equation, but it can be different for different applications. It's not just one equation for absolutely every single thing. So just keep that in mind. The t-distribution that we're going to be working with for the rest of this class is based on degrees of freedom. So degrees of freedom can be defined yet another way. It's the number of independent components minus the number of parameters estimated. The number of independent components minus the number of parameters estimated. So if I'm comparing means, my degrees of freedom is n minus 1. So I have n observations minus 1, which is my parameters estimated. We're looking at kind of the difference in means. And so I can calculate my degrees of freedom with a simple calculation, n minus 1, number of observations minus 1. But my degrees of freedom, when I start looking at regression analysis, if we're going to do basic OLS regression, ordinary least squares, you don't need to know that now. Some of you already know it. But when we do OLS regression, we're going to have a different equation. It's going to be n, number of observations, minus k, which is going to be our explanatory variables or our dependent variables, rather our independent variables. So our number of observations minus our independent variables, right, our explanatory variables, minus 1. And you'll understand a little bit more about that later. But one thing I want you to see, what's common in both of these equations? N, right? So degrees of freedom is related to n. It's a function of the number of observations. So the size of n is going to matter here when we think about our t-distribution. So again, let's be clear. Our t-distribution is a function of degrees of freedom. And degrees of freedom is a function of n, our number of observations. So when n changes, our degrees of freedom is going to change, which is going to impact our t-distribution, right? Do you see how these are all connected? Now we can see that right here because what I have right here is a t-distribution, but we have 3 of them. Why do we have 3 of them? Well, if you look at the right, you see it's because there are different degrees of freedom. Now, the black distribution is our t-distribution with infinite degrees of freedom. All right. So you're like, infinite degrees of freedom. All right, we're really just talking about converging, right, to our standard normal. So look at here, our black distribution. On the right, I have a note that says, hey, this is a t-distribution with infinity degrees of freedom, right, which is what? Infinity degrees of freedom. But look on the left, it says it's a standard normal distribution. So what does that tell us? It tells us that with really large n numbers of observations, our t-distribution is going to converge to the standard normal distribution. They're the same thing. But remember we said t-distributions are helpful when we have small n. Well, here we've got 20 degrees of freedom. Well, that's going to be a pretty small n to give us 20 degrees of freedom. Look what's happened to our t-distribution. Right? A little more uncertainty. Shorter, wider, more area in the tails. And as we get to an even smaller number of degrees of freedom, which means our n has shrunk, then we have an even shorter and wider distribution. So, you see that there's not just one simple t-distribution. It's a function of degrees of freedom. So that's important to understand. What that means is then, when we are using our t-distribution, what do we need to know? Oh, we need to know our degrees of freedom because we're going to have a table. Our t-distribution can be described in table form, but I can't look anything up if I don't know my degrees of freedom. So as we see, as degrees of freedom increase here, right, from red to blue to black, or from bottom to middle to top. So as degrees of freedom increase, we see that the standard deviation decreases. Now, guys, how do I see the standard deviation decreasing? Remember, standard deviation is a measure of what? Spread, right? Dispersion. Standard deviation means spread or dispersion. So, as I go from red to blue, bottom to middle, getting skinnier. So, my dispersion is smaller, my spread is smaller, my standard deviation is smaller. As we go to the black distribution, my standard deviation is continuing to decrease as we converge to the normal distribution. So as we said, as n gets large, we approach a normal distribution. A t-distribution approaches a normal distribution over n. So let's recap, but this is not my summary slide. There will be a few more slides, so do not close prematurely. As we've said, our t-distribution is a type of normal distribution. As our observations or our degrees of freedom grow very large, what did we just say? What's going to happen? What's going to happen to that t-distribution? Well, it's going to converge to the normal distribution. And we said this is useful when our sample sizes are not that large. Remember, with the t-distribution, we're estimating the variance or the standard deviation, and we're doing that based on the degrees of freedom. So our t-distribution depends on degrees of freedom, which depends on n. Now, our t-distributions give us a t-score. A t-score. Our t-score is the number of standard deviations from the mean in a t-distribution. The number of standard deviations from the mean in a t-distribution. So that seems like a lot of words, confusing, right? Well, we understand a t-distribution, right? It's that bell-shaped distribution. We understand mean. And we know that standard deviation is a measure of spread. So we're basically saying, how far away from the mean are we? Right? How many standard deviations from the mean are we? Simply means how far from the mean are we? Standard deviations is just a measurement, a unit of measure. It's like measuring in miles or measuring in feet. Well, in this world, we're measuring in standard deviations. And we can use this to test our hypotheses, right? It's much easier to illustrate this by example, so let's go ahead and do this as well. And that way we'll better understand a t-score. So let's say that we've sampled 20 students in 2 different classes. We agree that is not a particularly big sample, right? And we want to know if there's a difference between the group's mean scores. So we're looking at 2 means, class 1, class 2. It turns out the difference in means, and I probably should say the test score, I'm not being very clear. So we have test scores, and the test scores differ by 4.61. Sorry, so I keep saying score, but I mean test score. So can we just look at that and go, oh, test scores are different? Can we do that? Well, no. We can't just look at this difference of 4.61 points and say, hey, that's statistically significant. There's a difference. And the reason is that this difference could just be to chance, right? After all, I've taken a pretty small sample here, right? So this could just be by chance that I have a difference, and it might not really have any statistical validity. So we need to create a hypothesis test. And we're going to cover this more. This is just an example of kind of where we're going. So we create a hypothesis test with 2 possibilities. H sub 0, we call that the null hypothesis. And the null hypothesis is that test scores are not different. Now, normally, our null hypothesis is the thing that we want to reject. So I have a hypothesis that the test scores are not different. But to make this study interesting, right, if I'm doing a scientific study, that wouldn't be very interesting to find that they don't differ. So I have an alternate hypothesis, H sub A, that test scores are different. So I'm hoping that maybe I can reject that null hypothesis and prove that they are significantly different. But that's not what I'm going to do right here. But that's what we would do with this hypothesis. So again, we're just going to keep this very simple. Now, we have to subject this difference to testing. We're not going to literally do it, as I said. We're not going to do it right here. But what we're doing when we subject this difference of 4.61 points to testing, we're asking how likely is it that this is just due to chance? I don't have a very big sample here, so how likely is it was just kind of luck of the draw? So what we can do here is create what we call a range of outcomes. And this will be tied to what we do in the next lecture. But we can create this range of outcomes where we're 95% confident that our result, this difference of 4.61 points, is not due to chance. So we can create this range, and in that range, it would tell me that we are 95% confident that chance is not the reason we see these different test scores if our difference falls in that range. So we're going to find this range, and anything in the range means, hey, we're 95% confident that this is not due to chance, that this is a real outcome, that it's statistically significant. So we're going to see if our difference falls in this range, okay? It turns out the t-distribution gives us the tools to do this, right? And so you've heard me say a few times in a few different lectures this idea of, confidence. How likely is it? So this is kind of what we're working on towards our hypothesis test. We want to look at how confident can we be in an outcome. All right, so to be 95% confident, remember, we want to construct that range of values. And that range of values is going to be based on our t-distribution. So let's say that we find this range and it goes from 3.88 to 5.31, right? Now, we're not particularly worried about where these numbers are coming from, right? This is not our task for right now. Just trust me, we will get there. But we found this range, and anything in that range means that we can be 95% confident that our difference in test scores is not due to chance, that it's really a difference. So we'll do that part later. Where do the numbers come from? We're going to cover that later, don't worry. But let's now look at this graphically. So we see this t-distribution for the difference in the average test scores. And we found this upper and lower bound, right? So if you're looking for the upper and lower bound, look into that large red rectangle. And we had that range, remember, it went from 3.87 to 5.35, all right? And anything in that range, we can say we are 95% confident that we have a difference. But also see, guys, this range does not include 0, right? Look to the left, and I've got it in a red box for you as well. That would mean there's no difference in the means, right? So it's unlikely that the difference in the mean test scores is really 0. So what we said is that we can be 95% confident that our difference falls in that range, and 4.61 does. But we need the t-distribution to get those values. So I know this is a little confusing because we are just kind of setting ourselves up for what we're doing next. But you need to understand we have this thing called a t-distribution, that it is symmetric, it approaches the normal distribution. We can use this t-distribution to find this upper and lower bound, like what we just did here. Some of you are thinking, oh, this sounds like a confidence interval. Yep, you are right. So we're going to be looking at this upper and lower bound, which will tell us that there's a probability that's high, like 95%, if that's the level of confidence we're using, that our value falls in that range. So that's really where we're heading next. And we need the t-distribution to get there. If this is a little fuzzy, as I said, don't stress, because we're going to make this more concrete. So as I said, we're going to use the t-distribution for the rest of the semester. We're going to use it for hypothesis testing, and that will be an important part of the rest of the class. Now, there's a table version that summarizes the t-distribution and its characteristics, and we're going to learn how to use this table version. And I know some of you are thinking, really? We're going to use a t-table? Yeah, but we're also going to learn that the statistical packages give us this information as well. But gang, I'm going to defend the use of the t-table. Why? If you can read a t-table, if you understand it, then you can use any distribution that exists. But we'll work on that later. So for now, guys, let me know if you have any questions. This will be a little fuzzy. We're going to firm it up in our next few lectures, so don't stress about that. Have a fantastic day.